So we'll introduce Weierstrass's excess function. We'll define it in the following manner. Does this remind you of something? The appearance of this particular kind of function, does this remind you of something? Is this similar to something you have seen? Not just in this course, in calculus in general. Forget about the context of within which we are studying all of this. Sorry? Taylor series, fantastic. Taylor series around what point? Which is the variable? Sorry? Yes, you're right, Taylor series, it is. Yes? Yeah. The third variable, the third argument here in this function. Yeah. I've written it as a dot product so that you can also use vectors instead of this, but we'll for the much of it focus on singletons here. So we'll treat this, of course x is a singleton, y and w will also treat as singletons, but with a little bit of work you can always deal with them as inner products, and you can think of this y and w as vectors also of size n. Yes, it is exactly as you said. And that's exactly the interpretation I'm trying to arrive at. Before we derive conditions on this, it's important to understand what this essentially means geometrically. Now, suppose you know that a particular curve is passing through a point at x, given by y of x. Now, which direction should it thereafter go in order that the cost function is optimized? That is essentially decided by y prime in some sense, right? That tells you in the direction. Starting at that point x comma y, you could have chosen that y prime differently to go along different directions thereafter, right? That's one of the ways of looking at this decision making process, or looking at this problem as a decision making process in itself. I know there's no such thing here unless you think of this as a temporal process where you replace x with t, but nonetheless you can think of it like if you are at a particular point in this curve that's given by x comma y, so you fix up x comma y and you treat this now as a function of the third variable alone. That's doable. Think of this as an independent variable. Actually, that's not what Weierstrass did. This interpretation is what we are adding now. Having known about the maximum principle, it's easier for us to see. But 100 years back, Weierstrass was very close to arriving at a characterization of the maximum principle. It's just the fact that he did not look at it as an independent variable the way we are viewing it now, that it somehow got missed, okay. But the result is striking. What does this say? You fix up an x and y, so treat this exclusively as a function of its third argument. Yeah. In that situation, if you think of this axis, right, so suppose this is the point z and this is the point w. So this is probably the way in which it can be viewed, subject to your different choices of this third argument here. Yeah. So what happens then? What is this, do you think? What is this curve? If you fixed up W and Z as these 2 points, then how would you sketch it? Is that not the tangent here? Yeah. So essentially what I'm saying is that if you had drawn a straight line, this is a linear approximation. In the Taylor series, you're going only as far as the linear term. So when you said the Taylor series, you're absolutely spot on. You're going as far as the linear term and you're making an error in approximation, so to say, the one that you're familiar with, right? What's that error? So the actual function would have taken you to this point. This point over here. But this approximation is now taking you here. When I say the actual point and the approximation point, I can just put it here and just do this. Make sense? Right? So this is actually the difference. So this is the excess function. What Weierstrass's excess function based approach will tell us is that if you substitute z as y prime, okay, if you were to choose this third argument here, z as y prime, and you let w be any other possible choice, then this excess function would be greater than or equal to 0. Okay, we'll see, subject to time permitting, maybe in the next lecture. Perhaps we won't have time today, but in the next lecture we'll see how that pushes us one step closer to a statement in terms of the Hamiltonian. Is the sketch clear? Good. So now let us be a little more explicit about the type of perturbations that are allowed at non-corner points. Okay. So let's say this is A, this is B, so A comma 0, B comma 0 if you like. Suppose this point here, x bar, is a non-corner point. Not just the fact that x bar is a non-corner point, but as I said just a while back, we can always draw a small little interval, no matter howsoever small, around this, such that the entire interval does not contain any corner point. So suppose this goes all the way till x bar plus d. Okay. So the claim is that contains no, instead of claim I'd say the assumption is, and you'll always be able to find such a d, right? Okay, that's the standing assumption. So let's say this is the curve in question, that is the unperturbed curve. So the kind of perturbation we will allow on this interval is one that takes you away from the curve and then again brings you back at x bar plus d. So it will follow the original curve from A all the way through till x bar. Between x bar and x bar plus d, it will take some excursion away and then eventually again merge with the curve, the original curve, at x bar plus d. That's the kind of perturbation we'll be considering. So we'll consider a very specific kind of a perturbation. We'll say it varies in this following manner. So we'll say, so we'll characterize this by epsilon. Okay, let's take a point here which is x bar plus epsilon, because that epsilon is going to give us a handle like alpha in calculus of variations earlier, which told us or which kind of quantified the amount of perturbation. Here the same role will be played by epsilon, right? So what's it going to do? It's going to just take a perturbation like this, a kind of a straight line here. I'll write the explicit characterization of this perturbed curve so you'll know what we are talking about. Yeah, so it remains unperturbed outside of this interval. Okay, it's going to be y, whatever value y assumes at x bar, plus some w times x minus x bar. This is not an argument of w, yeah, this is just w times. So w is like the slope of this line here. Okay, for x belonging to x comma x plus, sorry, x bar comma x bar plus epsilon. And now you have to bring it back. So we're going to bring it back using a perturbation such that the perturbation is linear. So it is y plus some linear perturbation, which means that whatever value it attains here, what is the value it attains here? If you just plug in x bar plus epsilon here, it is going to attain y x bar plus w epsilon. Yes. So this point's coordinates will be x bar plus epsilon comma y x bar plus w epsilon, right? So we want to define this perturbation. We'll say, well, yx plus a linear perturbation. So, and it has to merge back with this. So of course it has to vanish. X minus d has to be there because at x is equal to d, again this merges with the original curve, and then the slope of this between these two. That's quite easy, isn't it? What's the slope? So you take the coordinate of this point. What is the coordinate of this point? It is x bar plus d comma y, sorry, actually this will be just d, right? I think I should just call it d. Forget about this x bar plus d. That will make things easy. I can write it as, yeah, I think that makes life easy. Otherwise I'll just have to carry this d as, it's better to have d as an absolute number. Yeah, I think that's better. Otherwise this length is entirely d, and out of which I have to take this as epsilon and this as d minus epsilon, which is a lot of pain. So let's just call this entire interval length as d. That's going to make, yeah, a lot of things simpler. So this is d comma yd. Yeah. Right? So what's the slope of this? This minus this divided by this minus this, right? That's the linear perturbation. I've already ensured that the perturbation vanishes at this point. So what's the slope? D minus x bar minus epsilon, and on top you have yd minus, what is the value here? Yx bar minus w epsilon. Agreed? So this is probably a correct characterization of the thing that we are wishing to build over here. So the actual curve is drawn in white. Let's just demarcate the perturbed curve. It will be completely overlapping the actual curve here. Then suddenly take an excursion like this. Then come back over here. And again merge back with the original curve. So everything that's happening to this perturbed curve different from the original curve is within this interval between x bar and d. That's the only portion where things are a little different. Everywhere else it's all the same. I hope the expressions are correct here, right? Okay. Here, third one. Why would you say that? Because at x is equal to d, this just vanishes. So it's just y of x. It merges with y of x. Okay, I'll just, this is x belonging to x bar plus epsilon to d. Yeah. Yeah, so what are you saying?
The first term should be y of d and it won't necessarily be a straight line.
Which one won't necessarily be a straight line? No, this curve is not a straight line because there's a perturbed curve. It's y plus some perturbation. The perturbation is a linear perturbation. So the perturbation is a linear one that vanishes at d. That's why I have x minus d. And because it has to be linear, so it's a straight line passing through the point this at x is equal to d, and it must vanish. So, and also the slope that it must carry is, because it joins these 2 points, so that's how I calculated the slope of this. So I took the y coordinate of this minus the y coordinate of this divided by the x coordinate of this minus the x coordinate of this. I suppose that's correct, right? Should be okay. Yeah? No, this is a different kind of a perturbation. This is where the entire curve is a straight line. Here, the entire curve is like the original curve plus a linear term. Here, the entire curve is just a straight line. It's not a, like, you cannot characterize this. You have to, if you have to characterize the perturbation here, that's more difficult to do here. I'm just giving you a expression of the whole perturbed curve. Here, the whole perturbed curve in the third interval, in this subinterval, it can be split up as the original curve plus a linear term. In this one also you could do that, but it's going to get only more complicated. I'm saying the overall function itself, this yx comma epsilon itself, is just going to become a straight line. So here it's different, but here it's a curve, the original curve plus perturbation, the perturbation is linear. Is that clear? The difference between the descriptions of these two. The reason why you have a yx bar here and you just have yx here. Here it's the unperturbed curve plus a linear perturbation. Here the whole thing is a linear function. The curve plus perturbation is linear. That's much more difficult to characterize in terms of curve plus perturbation is something linear. It's hard to do. You have to cancel out all non-linear terms over there and make sure that the entire curve is linear. Instead of that, we just say, okay, let it be just this function. And that arbitrariness is actually precisely captured by this w here. You can just choose any slope w. Is that clear? It's a good question. Yes, helps in building clarity. So now, what do you think is the approach going to be? What approach is going to serve us well here? We don't have the tools of calculus of variations at our disposal anymore. We are not dealing with C1 functions. We are not dealing with perturbations that are well behaved or nice anymore. So what do we do? As a trade-off, we now have a handle on this perturbation through this term called, what's it that characterizes the perturbation now? Epsilon. It's epsilon that now tells us the extent of the perturbation, right? If you put epsilon is equal to 0, what happens? Perturbation vanishes. You're back on the original curve. So essentially, if you're now going to vary epsilon along both positive and negative values, let's say, what's going to happen? Well, if you have to have negative values, then you have to build an interval on the left of x bar. similar things can be done. So what happens then? If you were to take the derivative of the entire cost function or cost functional as a function of epsilon and equate it to what exactly? What should you do now? As epsilon tends to 0, as epsilon becomes very small, shouldn't this derivative be greater or equal to 0? It should be non-negative at least, because it's telling you the direction along which the function changes. If your choice of y that you had made with epsilon is equal to 0 indeed extremizes or minimizes your cost function, then as you keep increasing epsilon one way or the other, you ought to be doing worse. So your cost is going to go up. So if you have a cost functional which is this j, and if you take the derivative of this with respect to epsilon and you let epsilon say tend to 0 plus, perhaps you should try and ensure conditions that give you this quantity being non-negative, right? Because in a Taylor series expansion, in terms of epsilon, you know that that's the first order term. Yeah. So the difference between the j evaluated at y x comma 0 and j evaluated at y x comma epsilon should be what? If it's a minima, if you're trying to minimize this, then it's going to be what? It should be negative. So therefore the difference between j evaluated at y with the additional epsilon, yeah, minus the j without the epsilon or the epsilon set to 0 should be positive. You should be increasing. The cost should be increasing as you apply a non-zero epsilon, right? So you should essentially try to ensure that this happens. Let's try and do that. This is different from calculus of variations. I want you to pause a moment on that thought. It is different from calculus of variations. We are no longer using this first variation idea. It doesn't work. The kind of perturbation we have here, it's not a smooth perturbation anymore. There was no corner point, but you've introduced points that are not smooth here. You've introduced a point like this, you've introduced a point like this through your perturbation, right? So of course you cannot hope to arrive at a good enough condition using the first variation approach anymore. You have to go back to first principles. Yeah, let's do that. Okay, so let's look at what happens with this orange curve, the perturbed one. Where do you think the difference is going to show up? See, along the interval from a to x bar, nothing else, no difference is there. So if you're trying to evaluate this quantity, is there any point in carrying out the integration of the cost functional over the entire interval? Doesn't make sense. Also, after this, post x is equal to d, you've again brought it back. This is not something that will happen when we derive maximum principle later. You'll see that's a stark difference. The approach is going to be similar, but we are not going to be keen on bringing it back anymore. Here we have brought it back. So in these two intervals between a and x bar and d and b, d and d comma b, there's no difference between the cost function subject to this epsilon. There's no epsilon dependency whatsoever. So the only part where you should be really concerned with this difference is in this small little interval between x bar and d, right? So let's try and evaluate the extra cost that is paid within this. So x bar to d here. X this is the term we should focus our attention on. Yeah. Just the second argument I have applied here is to show the dependency on epsilon. If you want to go back to the original curve, you just plug in epsilon is equal to 0 and you're back on the nominal curve, right? So if you want to apply the derivative with respect to epsilon, we should do it on this fellow. This is the only fellow that's responsible. Outside of this interval, as we've argued, it doesn't make sense. Let's just go one step further and split it up. Since we know explicitly x bar to x bar plus epsilon, the same object here, x, y, x comma epsilon, y prime, x comma epsilon dx plus x bar plus epsilon to d L x y x comma epsilon y prime x comma epsilon. It's pretty heavy in notation, but I'm sure you appreciate that beneath all this is not really very complicated. It's basically this orange curve that we are talking about. So when we do this d epsilon here, essentially this is what we are doing. Okay. Now, what do you think this term is? Well, you don't have to think, I've exactly written what it is. This, yes? So I might very well replace this with y at x bar plus w into x minus x bar. And what about this? This term is just w. So what immediately stands out is, does this argument depend on epsilon? No. Does this argument? Well, we've written it for the sake of representing the perturbed curve, but really if you write it down explicitly, this doesn't depend on epsilon. Yeah, that's the expression here. I mean, it depends very implicitly, as in the longer you choose epsilon, it will keep carrying on with that same slope. But really the nature of the curve within that domain is unaffected by epsilon. Yeah, same here. So when you take this differentiation under the integration sign, again our favorite tool perhaps through this course, the only thing that depends on epsilon is how long you integrate this. So by Leibniz rule of differentiation under the integration sign, what will this term give us? Quickly, differentiation of this term with respect to epsilon, that's 1, and then substitute this here. So what happens? That's just, see, this term doesn't get differentiated, no, because none of the terms depend on epsilon. The only thing that gets differentiated is this. So you then push in this argument wherever you have x here. So this is the Lagrangian evaluated at x bar plus epsilon. How about this? If you plug in x bar plus epsilon here, this is y x bar plus w epsilon. Yeah, this. Of course, the third term really isn't dependent on this at all. So it's just w, right? Okay, let's keep this in our stock. So hereafter, we'll just focus on this term. This one's taken care of. Okay, the entire burden now rests on the shoulders of this fellow. What about this fellow now? Well, one term will come out because of the differentiation with respect to epsilon of the lower limit of this integral, and if you differentiate the lower limit, of this integral, you will get a -1 because it's minus. Yeah, so this will give you minus and you have to substitute x bar plus epsilon here once again. Okay, but we are not done. Now, in this interval, things get interesting. Yeah, because now there are dependencies on epsilon. So what do? Differentiate and do all that rubbish? I mean, not rubbish, but there's a lot of stuff to handle here. There's things in the denominator that tend to get nasty when you differentiate with respect to epsilon. But we wonder if there are easier ways of doing this, perhaps more elegant ways. So what do we do? Yes? Of course, we keep the limits intact, differentiate each argument with respect to epsilon. Yes, and what happens? So first you have to differentiate this with respect to y and bring out the derivative of this with respect to epsilon, and then differentiate this with respect to y prime, the partial, and bring out the derivative of this with respect to epsilon. Now when you write this is already as if you've taken a partial with respect to x here, because you're not treating this as a function of two variables. The total differential with respect to x is like, when you're looking at it as a function of two variables, is like a partial with respect to x. Yeah. So we'll treat that, or we'll denote it, if you permit me this slight abuse of notation, not really an abuse, you're familiar with this. Instead of y prime, I'll now treat this y prime as y subscript x. Just for this particular case, yeah. Just allow me that much leeway for making the notation simpler. No other purpose. Okay. So what do we have here? We have plus, two integrations will come out, one owing to this, one owing to this. So we have integration over the same interval x bar plus epsilon to d L y x y x comma epsilon y x x comma epsilon with y epsilon, y subscript epsilon. Plus another integration over the same interval. Excuse the small handwriting here, but I'm sure you're familiar with this expression now, so you know what it is. It is L y prime, and I'm going to write x y x comma epsilon and y x x comma epsilon times y x epsilon, right? Double partial dx. Yeah, sorry about that puny little space over there. That's what there is to this term, right? I'm going to sort of cast aside some of these terms here and focus my attention on terms that I absolutely cannot do without. So now let's pull this term out here on this side. So I'll stop bothering with that term momentarily for the time being. So I'm going to just pull out minus L x bar plus epsilon y x bar plus epsilon comma epsilon and y prime x bar plus epsilon comma epsilon. Okay. And I'm going to also keep this integration. Should I keep it or should I dump it? No, let's keep this integration here. x bar plus epsilon to d. Please note this, I'm not going to finish this in today's lecture, so you have to prompt me in the next lecture when I come back and tell me what the right term is. Okay, x y x comma epsilon yx. So let me also make this as yx. Doesn't matter, yx or y prime times y epsilon x comma epsilon dx. So now the entire burden of this whole thing falls on, unfortunately, the term that I have written in the worst manner in this board, which is the smallest one here. Let's do proper justice to it. X bar plus epsilon to d Ly prime x y x comma epsilon y x x comma epsilon y x epsilon at x comma epsilon dx. What springs to mind immediately? What should you do? Our other favorite tool in this course, integration by parts. So when we come back in the next lecture, this is the term. Of course, we'll be considering these. These are things we have set aside for the time being. But now we'll use integration by parts. So to treat this as dv and this as u. So we'll again have that uv minus v du integration. Yeah, and what will happen? When you integrate this with respect to x, you will have y epsilon back and ddx. What happens? Something familiar pops up. Well, the Euler-Lagrange equation, right? And because of the fact that we are looking for a strong extremal, yeah, a necessary condition for a weak extremal has to be satisfied by a strong extremal. Necessary condition for a weak extremal is the satisfaction of the Euler-Lagrange condition. Therefore, the strong extremal must also satisfy the Euler-Lagrange condition. Therefore, that part of the integral has to disappear. So we'll be left with only one part of this integral. Yeah, and that's what we are going to deal with in the next lecture. Unfortunately, we've run out of time today. When we come back next, we'll finish this story and derive the entire condition in terms of Weierstrass's excess function. Thank you.